In this lecture, we're going to talk about a few ideas that I group under the topic network analysis. The first question we are going to ask is, what is the representational power of a neural network? So, a fully connected network defines a family of functions parameterized by the weights. And what we want to know is, what is the representational power of this family of functions? What functions can be modeled? And are there functions that cannot be modeled with a neural network? We're selecting a fully connected neural network for this because it's probably the first one that people looked at, and it's conceptually a very simple type of network. Let's first discuss the representational power of a linear network that only has linear layers. The network takes a vector as input, and in each layer, the vector from the previous layer is multiplied by a matrix. So the vector x in is the input to the network, and the vector x out is the output of the network. The first layer takes the input vector x in and multiplies it with the matrix w1. And as output, we have x2. The next layer takes x2 as input, multiplies with w2, the matrix w2, and obtains x3. And the last layer takes xl as input, where capital L is the number of layers in the network, multiplies with wl and gets x out. These capital W's are the matrices that define the parameters of a linear layer. We're kind of a bit glossing over this bias issue, but we'll just leave it at this precision here. So then when we put everything together, we note that x out is computed like this. All these matrices are multiplied, and then the vector is multiplied. And by the associative rule of matrix multiplication, we know that we don't have to first multiply w1 with x in. We can do multiplications in any order. In particular, we can group the multiplication by first multiplying all the matrices together. And since we can multiply all the matrices together, we can see that the output of multiplying all the matrices together is another matrix. So the combination of many linear layers is simply a single linear layer. So using only linear layers, the representational power of the network does not increase with adding more layers to it. Only using nonlinearities, the representational power of a network increases. If we have fully connected layers with nonlinear activation functions, then we can say that these networks with at least one hidden layer are universal function approximators. Loosely speaking, that means that any type of function can be approximated. However, as with most mathematical derivations, there are always certain restrictions and conditions that we are not really going into in this lecture. So for the graduate school versions, you have to look into one of these papers, the first Sybenko and the other one Hornig et al. Both of these papers are from 1989, and both of these papers establish something very similar. And these papers are readable by graduate students, but they use some amount of mathematics. So here's a quote from the paper. We show that arbitrary decision regions can be arbitrarily well approximated by continuous feed-forward neural networks with only a single internal hidden layer and any continuous sigmoidal nonlinearity. So the key things here are that there's only a single hidden layer and you need an appropriate nonlinearity. So in this case, there's this sigmoid nonlinearity chosen. Even though we're skipping the graduate school version, what I would like to show is the high school version of the proof that basically shows the construction of how an arbitrary function can be constructed. This version is extremely nice. This person did a really great job. I will link his short video that I highly recommend also in the playlist, and I will show something from his interactive book, interactive webpage about how the construction works that shows that the network can approximate arbitrary functions. The idea is that the whole thing is done by construction, and therefore the idea is very, very intuitive. And even if, of course, I hope, and I'll put this as a reading assignment, you read the graduate school version, the high school version should be a great preparation to see how a proof can be constructed more formally. Before looking at the link on top here, this online book, let's still read this simple version that says that given any continuous function f of x, so we have a function f of x, and then we would like to have some epsilon greater 0 that tells us basically how well we would like to approximate, then there exists a neural network that computes a function g of x parameterized by theta, and it has only one hidden layer with a reasonable choice of nonlinearity, again in this particular choice sigmoid. And so what is possible is that we can construct a g of x with the neural network such that f of x minus g of x is smaller than epsilon for all x. So we look at this function here, and let's say we have some arbitrary function where on the x-axis this is the input, and then on the y-axis is the output. So we have this function f of x that we would like to model with a neural network. What we do then is we are going to start with a very simple neural network here, and to start out with, we'll forget the input down there. We'll just have this node here, which is an input x, and this input x here will vary along this x-axis. So basically we'll just try all the possible x's, and then we plot the output of not the complete network, because we forget this, we also forget this, but we'll plot the output of this one neuron. And so how the computation is constructed here is that we will compute w, so this is 8 here, w times x plus b, so in this time, so here we have 8 times x minus 4, and then we apply the sigmoid nonlinearity. So now, since this is interactive, we can see what happens if we change this bias term. We'll make it larger, no, smaller and larger. So it's not totally clear maybe what happens, but it looks a bit like this would be a shift. So changing the bias, we will shift this sigmoid ramp to the left or to the right. And then the weight will make the sigmoid function more or less steep. So let's try to make it very steep. And now let's try to shift again, so we can see that we can build something that's a pretty steep ramp with a single neuron and the nonlinearity. So continuing with this figure here, if we keep this W parameter big enough, then we can make this whole thing almost into a step function. So if W can go almost to infinity, then this will kind of approach a step function. So looking at this example here, this tells us that the position of the step function is at minus b divided by w. So let's keep w at 100. So now we can move b around to change the position of the step. And the step is always at this position given by this equation. So we can also change w, but somehow, let's say we keep w large, and then we'll just parameterize the whole neuron with a single value s, which is down here. So we'll just move the step to the left and to the right with one parameter s. And we keep w high such that it is a pretty sharp step function. Next, we add a second neuron. So the old neuron was up here, which is parameterized by S1 equals 0.4 now. And then we add a second neuron with S2 is 0.6. Again, the weights that get multiplied here are kept constant and very high. And then we can change the position of these step functions, and we're going to add them together with linear weights. So this neuron simply adds these two step functions together, and each of them with a weight which will determine the height. So this parameter S1 will move the first step function to the left and to the right. Let's keep it to the left. And the weight will make the first step function higher and lower, and the second weight will just change the second step function higher and lower. In particular, we note that changing the second step function to give it the weight minus whatever W1 is, we can build a box. And then we can say with S1, where does the box start? And with S2, where does the box end? Again, linking these variables together, we can basically parameterize in the way that we have one parameter for the box height, which keeps these two weights linked. So the first link has the h parameter, and this second link is minus h. And then we have the starting position and the end position of the box here. Now we add two more neurons, and then we obtain a second box. So this neuron on top and the second neuron with this h parameter define the first box. We can change again, change this, and this neuron and this neuron together with this h parameter defines the second box. Again, we can make it change the width and height position. So then next we can add more boxes and also link the spatial positions of the boxes. Maybe the first box goes from 0.0 to 0.2, the next box from 0.2 to 0.4, and so we'll just have one parameter for each of these boxes that are now joined together, and so there are no more gaps. And then, kind of reminiscent of Riemann integration, you can already guess that by making the boxes smaller and smaller and controlling the height of the boxes, you can start to approximate an arbitrary function. Going to two inputs, and doing this in 2D, you can again build something like a step function. Now it's like a step function in 2D. You can build one in this orientation, and down here you can build one in another orientation. And then skipping a few steps, you can build something like towers. So here you see one tower being controlled by this parameter, and then here another tower by this parameter. And so again, you can kind of imagine how adding more and more towers, you can approximate an arbitrary function. There's still open questions, such as now it seems we have two hidden layers, so you have to find some way to merge this together and build this construction with a single hidden layer. And also you still need to think of how can you extend this to arbitrary dimensions. But we'll leave it here, and we'll go back to the lecture slides. Of course, we can note that this type of proof by construction does not create a reasonable network in practice. This analysis work has been extended in a few directions. For example, it can be shown that also the derivatives of the feed-forward network can approximate the derivatives of the function arbitrarily well. And this is the paper for this. Further, the original proofs were for a class of activation functions like sigmoid. And then later on, there are extensions to other functions that also includes, for example, the ReLU function. So another question is, again, very loosely speaking, like how big does this single layer need to be? And there the answer is, of course, in the worst case, we have some exponential explosion of the hidden units that is required to approximate a function. So people also try to answer, like, how do these resulting functions look like? Maybe on the number of linear regions of deep neural networks. So these maybe piecewise linear networks are obtained from ReLU or max out nonlinearities. And these networks can represent functions with a number of regions that is exponential in the depth of the network. So that says that the depth definitely helps for creating more and more linear regions. So there's one equation given, that is D are the inputs, depth layers denoted by L, and N are the units per hidden layer. So this gives us then something on the order of N to the power of D, that is hidden units to the power of a number of inputs, and then we have N choose D, that is units per hidden layer, choose the inputs, and then to the power of D times, and here we see the magic of the layers, L minus 1. Additional information can be found in the deep learning